Okay, welcome. So in this video, we're going to start talking about finding areas between curves using calculus. And so we're going to start with the idea of partitioning the graph. So we want to find the area between this curve and that. Hold on a second. Forgot the label. There we go. Okay, so what we want to do is we want to let f of x and g of x be continuous functions over a closed interval ab, such that f of x is greater than or equal to g of x on the same closed interval. So we want to find the area between these two curves on that closed interval. So what we're going to do is we are going to partition this graph into rectangles. So we're going to estimate the area by using the rectangles. So what we're going to do is we're going to subdivide this interval into, let's say, n partitions. Okay, so we're going to divide it up into n partitions, n intervals. So for x equals x of 1, x of 2, all the way to x of n. Okay, so that's what we're going to start with. Okay. Now, for each one of these x's, so we're going to actually have a closed interval, so that will go from x of 1, right, to x of 2, and then another interval from x of 2 to x of 3. And then so on and so forth. So basically we're going to have x of n minus 1, right? Oh, actually, x of n minus 1, which actually, this should start at 0. So let me add another one. So that should start at 0. Okay? So the general interval is going to be x of n minus 1 to, no, not n, I. To x of I. So we're going to have these rectangles. And so what we're going to end up doing is we're going to pick a point on these intervals, let's say x sub star. So x star is going to be our sample point. And we're going to pick the sample point within each interval to help determine the height of the rectangle. So again, we're partitioning this interval into equal partitions, so their rectangles are the same width, and then we're going to pick a sample point x star within each one of these intervals, these subintervals. And what that's going to do is it's going to help us determine the height of these rectangles. Right? And so what we're going to end up having is these rectangles. Again, my picture notwithstanding. And so we're going to have all of these n subintervals with these n rectangles to help us estimate the area under the curve. Now, what we're going to end up having is one of these rectangles, is going to have three values. So we're going to have the width of each rectangle. The width of each rectangle is going to be delta x. Okay, the change in x, right? Now, again, each one of these rectangles by construction are going to have the same delta x, right? Because that's what we did. How do we get the delta x? Well, it's going to be b minus a divided by n. That's how we're going to get our delta x. That's the definition of delta x. And that's why it's always going to be the same. We have how many subintervals do we want? We want n subintervals. And we need to find the length of the interval from A to B, the closed interval from A to B. So we're subdividing our interval into subintervals, and so the width of each subinterval is delta x. Okay. Now, once we find our choose our x star. Now, x star could be the left end point, the right end point. It could be the midpoint, right? So we've seen those in using the trapezoidal method and things like that. You've seen those before. And so I'm just reviewing some of this, right? To introduce the idea here. So if I have my x star, so what we're going to do is I have my delta x. So to find the area of this rectangle, I need to find the height of this rectangle. I've got the width. Now we got to find the height of each one of these rectangles. Well, the height of the rectangle is at x star here, evaluated at f. So it's going to be f of x star here, and the base, the base is located where? That's going to be located at g of x star. So how do we find the height? It's going to be the top minus the bottom. So wherever this value is, right? This y value, and wherever this y value is located, right? So again, that's so this is equal to f of x star, and this y value is equal to g of x star. So if we subtract those two, we get the height of that particular rectangle. So in general, that's what we're going to do for all of these rectangles. So the height of each one of these rectangles is going to be equal to f of x star minus g of x star. So, if we want to approximate the area then, what are we going to do? We're going to sum up all of these rectangles, right? So let's do that. So the area between these two curves is approximately the sum, right? So we're going to sum up all the rectangles for all of these rectangles. Well, how many rectangles are there? Well, it goes from I equals 1, right? To n. Okay? And so what's the height of each rectangle? Well, that's determined by f of xi, right? F of xi star. Minus g of x sub I star. And then, of course, what are we doing? We're finding area. So we're going to multiply by delta x. So this is the height times the base, right? So each rectangle is going to be base times height. So this is going to be the area of one particular rectangle, and we're summing them up over all n rectangles, and that's going to give us the approximate area between the two curves. Okay, so this is a Riemann sum, right? We've seen these before. So what we're going to do is we're going to take the limit of this thing. So if I want now here's the thing. This is an approximation. So if I take more and more and more rectangles, my estimate is going to get more and more accurate, right? Because the smaller the triangles, or excuse me, the smaller the rectangles, the less of an error I'm going to have. Because see how part of my rectangle is above and part of my rectangle is below the curve? And so that's going to be an error. But if I take more and more rectangles, I'm going to get a more and more accurate number or estimate of the area. So if I want the exact answer, then I'm going to take the limit of this sum as n approaches infinity. So what happens then? Well, so A, now this was an approximate, so A equals the limit, right? As n approaches infinity of this sum. I equals 1 to n And so what happens? Well, as it happens before with Riemann sums, as we take the limit of this thing, well, the summation symbol becomes the integral. So because what I'm doing is I'm going from A to B, so now this is going to equal the integral from A to B of what? F of x sub I but now we don't have I anymore because we're taking it to infinity, so now it's just going to be f of x minus g of x dx. So the delta x becomes the derivative, differential, dx, and we're done. So that becomes the way we're going to find the area between two curves. And so in the next one, I'm going to introduce the next theorem. So in the next video, we're going to introduce the next theorem, and then we'll go do some examples. That's it.